Now we're going to talk about the convergence set or the interval of convergence. So just as before, when we were talking about the radius of convergence, if a numerical value is substituted in for x in a power series, then the resulting series of numbers, of constants, could either converge or diverge. And so we have to determine the set of x values for each given power series for which the power series converges and has the same outputs as the function. This interval, these x values, are called the convergence set, or equivalently the interval of convergence. So the process for finding this set, it begins exactly like the process for finding the radius of convergence. But now we have to consider the entire interval, not just how far away from that center point that we can go with our x values like we did with the radius of convergence. So let's find the convergence set for this series. This is actually a series that we've already found the radius of convergence for, so we will quickly do our work for the radius of convergence, because we can't get to the interval of convergence without finding the radius of convergence first. So the work for both of those begins exactly the same. So let's get our n plus first term that looks like that. Let's plug everything into this limit that expands x to the n times x, n plus 2, 2 to the n times 2, x to the n, n plus 1, 2 to the n. So it looks really complicated, but once you get it all plugged in there, it's not. We cancel everything that is acting like 1 near infinity, and we get that for the answer of our limit. Now, I could go ahead, if you wanted to, and say, okay, that cleans up to this, so that means this is a constant as far as n is concerned, but we just did that work. So hopefully you can see that. Remember, we are going to converge when this is less than 1. So the interval, there's the radius of convergence. This is why I say we have to go through the radius of convergence to get to the interval of convergence. So using algebra, the interval over which this series is going to converge looks like this. Now, we're not done yet, because just as I said on the last slide, what we've done now is we've found values of x from -2 to +2, where this power series will have the same outputs as the function that it was built around. However, we don't know what's happening at the endpoints on this interval for x values. That's the biggest difference between the radius of convergence and the interval of convergence, or convergence set. Now we have to determine what's happening at x equal -2 and at x equal 2, because we don't have them included on this interval, and one or both or neither of those may actually be x values where this series does converge. So this is exactly what your work is going to look like. We're going to show the AP reader which endpoint we're considering. First, we'll consider the left endpoint. Now, when x equals -2, what we're going to do is we're going to go back to our series, and we're going to plug that value into our series for x. Right up there at the top, I'm plugging -2 in for x. That's how I'm going to see if this series converges when x equals -2. Wherever there's an x in that general term, I'm going to write -2 instead. And I'm showing the AP reader what I'm doing. Now, the first thing I'm going to do is clean it up. and see if I can determine what type of series it is. Is it geometric? Is it alternating? Is it harmonic? So the first thing I'm going to do is clean it up. Look what's happening in the numerator. Would you agree that the numerator can be written equivalently as -1 to the n times 2 to the n? Exponentials break up over multiplication, so I can break that up if I need to. And clearly, here's why I believe that I need to. That's acting like 1. This series in n, this general series, not power series, is an alternating series. And it is this alternating series. Well, how do I determine whether an alternating series converges or diverges? I run the alternating series test. This is why we learned all of those. Well, it's one of the reasons why we learned all of those tests. We're going to see them all over the multiple choice part of the test, but for free response, this is where it's going to show up most often when we're testing the endpoints of this interval to see if it converges or diverges or not. We have to use a good test. The alternating series test says take the positive portion of that nth term and plop it in this limit. If you get 0 out of that, your series converges. And this is why we have to qualify which test we're running. I ran the alternating series test. I found that this series, when x equals -2, converges. Now I'm going to come over here and I'm going to do the same thing for when x equals 2. I'm going to go pick up the original series. Everywhere that there is an x in that original series, I am going to write 2 instead. Then I'm going to clean it up. Notice that I never drop my series notation. I don't just pull that nth term out and start messing with it. What my work looks like is exactly what your work must look like. I am modeling what needs to be shown on the AP test. This is exactly how your work needs to look. So this cleans up to a positive series. And it's a positive series that looks harmonic to me. It is not the harmonic series. Be very careful. I have students every year that are like, oh, well, for large n, that's acting like 1 over n. That's diverging. That's the harmonic series. I'll just say, this is the harmonic series and it's diverging. That's incorrect work. This is not the harmonic series. Yes, it's acting like it for large n, but this points me to a test. And the test that it points me to is finding a b sub n for large n that acts just like my series, showing the AP reader that I recognize how b sub n behaves. This is the harmonic series. This does diverge. Now that I have a series for large n that behaves just like my series, I can run a good test. Series that involve only powers of n, polynomial powers of n, are perfect for the limit comparison test. So that's what I'm going to run. The limit as n approaches infinity of my unknown function over my known function. Please run a good limit. Clean it up algebraically. This is infinity over infinity. I can run L'Hopital's and I'm going to get 1 for an answer. That is an excellent result for the limit comparison test. So this series diverges because b sub n diverges. Getting 1 out of that limit in the limit comparison test says a sub n acts just like it. So this diverges by the limit comparison test. Is that the only test that I could have run? No. No, and therein, lies the struggle that students have when it comes to series. There's a lot of decision making to be had. Someone else might choose to run the direct comparison test. Someone else might choose to run, this is a good candidate for the integral test. So it just depends on which test you want to run. The harmonic series is quicker, it's more straightforward. I have done this long enough that I recognize when my series involves only powers of n, that it's an excellent candidate for the limit comparison test, and I will get a real number value out of that limit when I put it in a ratio with a b sub n. All right? This is why we learned all of those series tests. Now we're not done. We haven't answered the question. What is the convergence set or the interval of convergence? Well, we know all of the values in between -2 and 2 are included. Now we know whether -2 and 2 are included. And it turns out the interval of convergence is including -2, but not including 2. There is our interval of convergence. This series converged when x equals -2. That means when I plug -2 into my series, I get the exact same output as I get when I plug -2 into the function. This says +2 does not yield me the same output from the power series as I get from the function. It's not included in the interval of x values for which this series acts like the function. That's what the interval of convergence is. Okay, I have another example for interval of convergence. This is huge for us. This is almost always either part A or part B on our free response series question that we're almost certain that we're going to get on our AP exam. So this is non-negotiable. This you have to know how to do. So I want to work one additional example. I don't think I'll get all the way through it in this video, so more than likely we'll have another one. If I get cut off, just look for the next video. All right, same kind of idea. Here we are in K. What's your notation? I don't care anything about the alternating term. I could care less about the alternating term. It is not going into my absolute ratio test, so I'm not even going to pick it up. Everything now is k plus 1, not n plus 1. Watch your notation carefully. Here we are at the end of the school year. I think I've made believers just out of about everyone that notation makes a huge difference. We are taking k to infinity, not n. So we are going to have x to the k times x over 3 to the k times 3 times k plus 2 multiplied by the reciprocal of a sub k. There we are. Let's cancel common terms at k approaching infinity. Those two terms will even cancel. There's nothing left but constants here. The result of this limit is the absolute value of x over 3. We are going to converge when that is less than 1. We have a radius of convergence of 3. We have part of our interval of convergence or convergence set that is from -3 to 3. Now we have to see what's happening at the endpoints. Is -3 included in the interval? Or is +3 included in the interval? I'm near the end of this video, so we'll pause. We'll have a short video to finish this up. So look for one additional video.